Here's another situation which we have a force in newtons depicted in the vertical direction, position in meters in the horizontal direction on a vertical horizontal coordinate plane, and a trapezoid at some unspecified position, but in which the trapezoid has a width of 0.2 meters, 0.2 meters in this direction, and the altitudes represent 4 newtons and 6 newtons. You should quickly work out the slope and the area of this trapezoid and label it. It should be clear that the slope is 10 newtons per meter and the area is 1 newton times meter. Now we want to talk about the interpretation of these results. Now just quickly, in case you had trouble getting those results, the rise is going to be 2 newtons, the run is 0.2 meters, and when you divide newtons by meters, you get newtons divided by meters, or newtons per meter, and 2 divided by 0.2 is 10. Those calculations should be immediate. If you had to use a calculator for that, put that calculator away and don't touch it for a while. Okay, and the area, well, the average of the 2 altitudes, giving you, of course, the altitude that you would have for the equivalent rectangle, is 5 newtons. Represents 5 newtons. The average altitude is 5, and that represents 5 newtons. And you multiply that by the width, which is 0.2 meters, and you get 5 times 0.2 is 1, and you have newtons times meters. Now, what is the interpretation of this? To interpret the slope, we interpret the rise and the run. What does the rise mean? What does the run mean? Well, the rise is our 2 newton change in force, or at least rise represents the 2 newton change in force. The run represents the 0.2 meter change in position. So the slope represents the change in the force, which I'll designate as delta F, over the change in position, which I'll designate as delta X, using the familiar convention that delta means change in. So delta F is a change in the force, delta X is the change in the position. And that is just the average rate at which the force changes with respect to position. This means that as we change our position on the average, at least between these 2 points, for every meter of change in position, we have a 10 newton change in force. Now, of course, we don't have a 1 meter change in position here. We have just fractions of a meter between here and here. But this would mean that, for example, if you change the position by 1 centimeter, which is 0.01 meters, then at 10 newtons per meter, you would multiply that by the 0.1 meters, 0.01 meters corresponding to 1 centimeter, and get the change. And let's just kind of write that down. So the question would be, for a typical 1 centimeter change in position here, what would be the change in the force? Now, in terms of the slope, which is the average rate of change of force with respect to position, the 0.01 meter change in position implies how much change in force? Well, if the force changes at the rate of 10 newtons for every meter, then a 0.01 meter change in position is going to give us 0.01 times the 10 newton change. Now, that's going to give us 0.1 newtons. Now, more formally, we write that out as the change in the force is 10 newtons per meter multiplied by 0.01 meters. We can see that the meters rearrange and give us unity and so forth, leaving us with units of newtons. And 10 times 0.01, of course, is 0.1. Now, that correlates with a more intuitive calculation. 0.1 meters is 1/20th of this 0.2 meter distance here. And the change in force over that 2 meter distance is 2 newtons. So we expect that the change in force would be 1/20th of our 2 newton change in the force, corresponding to the 0.2 meters. And that's going to give us, again, 0.1 newtons. that will formalize this a little more, but this intuitive calculation corresponds to the slightly more formal calculation that we get here.